I mean everything we know about right angle triangles. So that includes the Pythagorean theorem. And if it's sort of rusty in your brain, you're like, oh, I remember I was good at this, but you don't kind of remember, I cover it in my examples. So coming up today, the Pythagorean theorem in a question, yes. And there it is, a squared plus b squared equals c squared. Very ancient theorem, yes. Also, SOHCAHTOA, and the same thing. If you're like, oh, I sort of remember this, I was good at this. Or maybe I wasn't that good at it. Totally reviewing SOHCAHTOA today. But there it is on the sheet, so if you're looking back at it, you can see. When doing a right angle triangle, now note it, that may be one little thing that maybe went past you in grade 10. This is for right angle triangles. So, when you want to do SOHCAHTOA, you're only doing that on right angled triangles. If it's not right angled, we need another set of tools. We don't have to worry about that today just yet, but something to think about is that you're not going to get hypotenuse, opposite, adjacent when it's not right angled. That's specifically right angled triangles. And here they are. Sine of theta is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Are those names made up just to torture grade 10 and 11 students with weird names that don't make any sense? And the answer is no, but it's hard to see for a long, long time where these names could possibly come from. And there's a hint there. Sine, cosine. You know, it's like it's the opposite of sine sort of thing. And tangent, well, you might have seen tangent in other lessons, a tangent line. So that really is the tangent line, but it takes a long time before these names make any sense. So we come up with a cute memory tool. People make fun of me because I say SOHCAHTOA, and people say, no, you should say SOHCAHTOA. So I'm trying to do better. If you really want to remember this, it's SOHCAHTOA. And all this does is help you remember which pair go with which ratio. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tan is opposite over adjacent. So apparently that's all you got to remember. As long as you remember this phrase, or so this word here, this acronym, then you have all your stuff you need to do SOHCAHTOA questions. Does this ring a bell? Hopefully, yeah? Should have seen the first time I taught this after coronavirus, because a lot of people during coronavirus, when they got to do their tests online, didn't really memorize this. They just kept looking back at it. So we went to teach it again. They're like, I don't remember it at all. So it's gotten better now. Things have gotten better because, well, what grades were you in when coronavirus came in? You guys would have been like grade 7, 8. So that's not so bad as it was when in the high school things. What? Why is this all the way down here? Here's the first example. In triangle ABC, angle B equals 90 degrees. Well, that's good news. Here's what happens. As soon as you see 90 degrees, you're like, okay, here's what comes off the bench. It's right angle triangle. So Pythagorean theorem's in if we need it, and SOHCAHTOA's in if we need it. Those are our two weapons, and the only two weapons you should need. Okay? That's a slight lie. There's one more weapon out there, which I'll talk about, but it's really old news, but I'll bring it up. Okay, so I need a triangle here. So I'm just going to draw a triangle. Oops. Straight line. Right angle triangle. Some questions give you the diagram, some don't. And so angle B is the 90 right here. And they didn't say where to put A and C, so I'm going to put them like that. But you'll get the same answers as me if you went to do it and you put the A and C in the opposite spots. So we'll label what we know. A is 18.6. And B is 11.3 centimeters. Love labeling diagrams. As you're doing these, great move is to label the diagram. It says solve the triangle, find all the unknown sides and angles. Now let me just go through this as if we were reviewing for your grade 10 quiz on this. Yes? And the thinking would go like this. You'd go, first, can I find another side? And the answer is, not with the Pythagorean theorem, you can't. Because Pythagorean theorem requires that you have two sides and get a third. But you can use SOHCAHTOA. So based on this angle, I label my sides. I have this angle, so this one is called hypotenuse. Now if you have questions, do not be shy, because this labeling is just a little bit strange if you don't remember it exactly. Now, since this is 18.6, I'd suggest if you have trouble with labeling, what you do is you draw an arrow that goes straight across the triangle like that to remind you that when we're looking for opposite side, we mean opposite the angle. We truly mean that this will be the opposite side for this question. And then the one along the side will be adjacent. Adjacent means beside. So adjacent is right beside the angle there that we're working with. We're working with the 18.6 here because that's what they were given. Could somebody else do this question differently? Yes, and I'll talk about that in just a minute because you could look at it and go, I see another way. And I'm going to talk about that. I'm going to throw it in there. But don't think that means opposite is the bottom side all the time. No, no, no. Opposite is just where, based on the angle you're using, which one's opposite to that angle. Okay? So I look at that and I go, okay, I got to use the thing I know. I got to use the hypotenuse. And then I can either go after opposite or adjacent. And this question, it doesn't matter which one you go after first. Just in the interest of using sine to begin with, I'm going to go after opposite first. And that's just a choice. You could go after adjacent first if you wanted in this question. So I'm going to go after opposite. So that tells me I'm trying to get opposite and I have hypotenuse. That's enough, apparently, to tell me which of the three in SOHCAHTOA to use. Because I look and I go, which one has something I want and has something I have? That's what it comes down to. That's the only decision you have to make. And it's sine. Sine has something I want to solve for opposite, and something I already have, which is hypotenuse. So I write that down. Sine of A equals opposite over hypotenuse. And the only reason I wrote that is because now I've made a decision which one can help me. Then I fill in the things I know. I know 18.6, so sine of 18.6 degrees is opposite, which I don't know. I don't know what that side's called. And you could label it a lot of things. Some people might label this little a if they were really experienced with trig, because it's opposite the big A, so we call it little a. But for this question, I'll just call it BC. That side over there called BC. That's what I'll call it. And then the hypotenuse is 11.3. That's supposed to be the only tough part of SOHCAHTOA. Supposed to be. From there, you're just solving the little equation you built here. Keeping in mind that sine 18.6 is not a mystery. I can't do sine 18.6 in my head. I could sort of guess about what the answer would be. I could give you a close answer, but I don't know what the number is. I need my calculator for that. Because especially 18.6, no one's going to know that. So I'm not bothered by this. Sine 18.6, I'm just going to type that in my calculator at some point. So the only thing I'm going to do is try to isolate BC, which if it's divided by 11.3, I can move that over and make it multiply by 11.3. And if it offends you that I'm solving for BC on the right, then you should do it the other way. You should flip them around and write BC equals 11.3 sine 18.6. Now, let's go to the calculator now. And I want to show you on the calculator how to type this in, because there is one little thing that could go wrong here. Bring my calculator up. And I want to type in 11.3 sine 18.6. Now, you have to be in degree mode. There are different modes the calculator can be in. They're called degrees, radians, and gradients. Those words can totally scare you at this point. What's radians? What's gradients? Why would we need a different setting? Why would they put that on the calculator? Is that just to mess us up? No, no. There's more to the story coming in grade 12, advanced functions. Okay? But for now, we're always going to work in degrees. So anytime you've got to look up and see at the top. Mine says DEG. Yours might only say D for degrees. So take a look. Now, every calculator is different how you switch it from into degree mode. So if you're not in degree mode, you should call me over. Mine is on mine, I think it's a DRG button. I got to look all around for it because like I say, every calculator is different on where they put this thing. And looking, there it is, DRG. So mine, I got to hit second function decimal point. Oops. Second function decimal point. And that switches it to rad mode. Apparently that's a different mode. It's not in degree mode anymore. So then I hit second function, and that switches it to grad mode. Yours might say G instead, and then over to degrees. Sometimes it's in one of the little setup menus. In the Casio ones that are so popular now, it's a shift mode, which is setup, and then you hit 3 for degrees. Okay? So that's different calculators do it differently. One of these sharp ones. It has a DRG button, so you just hit DRG and just keep hitting it until it says degrees. Okay. After doing that, to make sure you're in the right mode, and it is not funny to reach over the day before the test and put someone's calculator into a different mode. That isn't, it sounds funny, I know, but it's not funny to do that. 18.6, type it in, see if you get what I get. See if we agree. 3.6. With no other information, go with one decimal place. Now, I don't know if your teacher made a big deal about this last year, but I think it's a really important thing. As soon as you solve for something, put it on the diagram. That really helps in the thinking of what to do next. Clearly, my diagram isn't to scale, nor do we make much effort to make the diagrams to scale. That looks like, in my picture, it looks really pretty long that time. Well, and then the reason is 18.6. I should have drawn that angle a lot smaller. You know, I made it pretty big. Okay. Any questions on that? Don't be embarrassed if there's questions about that. That's not something people walk around and think about every day. And if you had grade 10 academic math first semester last year, you probably haven't even thought about it in 10 straight months about how this works. So if you have questions, now's a great time. Kyle, question?
I know you wrote like BC.
Yes?
Can we just keep it as opposite? Or?
I don't know if I want to keep it as opposite, but some people will definitely call that A if they remember their labeling for non-right angled triangles. They might go with A there, and they might be happier calling that A instead of BC. But I don't know, leaving it as opposite is the right move. We want to get yeah. Okay, so that was step one. Now this says solve the triangle, and solve the triangle means find everything. And all I've done is find one of the sides. But by having a second side, who's jumped off the bench to help? I have a second side now. So what weapon now has jumped into the game now that I have two sides?
A squared plus B squared, or like C, like whatever it is.
Pythagorean theorem, and maybe that even is like a little rusty on the whole thing. When can I use Pythagorean theorem? Because the way we teach it sort of sets you up for failure, because we teach you Pythagorean theorem, and then we give you a whole bunch of questions where the only thing you can do is Pythagorean theorem, and you go, okay, good, I'll know when to do it. No, it's not quite that easy. You got to look at the question and go, do I have two sides to make Pythagorean theorem useful? So this time I do have two sides. So what I'm going to do is write, now I might write it differently than you write it. I don't usually write it with a C there, me personally, because I'm a grade 10, 11 teacher, and I'm always worried that people are going to write things in the wrong spot. So I write it this way. I don't use a C there.
Why?
Why? Because I want people to remember the hypotenuse is the one by itself over here. Because the A, B's, and C's are in the wrong spots in this question. I mean, A, B, and C was just us writing it down going, say there's a C here. It's not like, oh, there's going to be a C there. The hypotenuse is always called C. That's not true. And this question, the C in my question I've just done, if I was going to label the C, it would be the adjacent side. That can really mess you up. That's why I like this version of it. Hypotenuse squared equals A squared plus B squared. And then people make less mistakes. The hypotenuse squared is 11.3 squared. The A squared, I'm going to use it as 3.6 squared. And then I'm going to call this B squared, which is actually the adjacent side. Technically speaking, it's not the B squared. It's the C squared, because of the labeling of this triangle. Yeah, that's a little bit difficult. So that, instead, to make it even, I'm not trying to make it confusing. I'm actually trying to get to the bottom of what might confuse you. I'll just call that AB, and then I don't have to worry about the C's, the A's, the B's, and just go, I'll just name them by their sides there. That takes a little bit of practice. So that means 11.3 squared minus 3.6 squared. That's where the minus comes from in the Pythagorean theorem. So then I type that in my calculator, 11.3 squared. And when you did this in grade 7 or 8, you might have wrote down what 11.3 squared was, and then you wrote down what 3.6 squared is. Maybe we're a little more advanced than that now, where we can just do that and get the answer, 114.73. Now that is very strange, isn't it? One side's 3, one side's 11, and the other side's 114?
Can't triangles be like, oh wait, don't you have to thingy it?
Thingy it?
Yeah,
Is that what you said?
So you get the line, it's like that.
Anybody know what this thingy's called?
Square
Square
root.
root.
Probably 11.
Easy to forget. Yeah, around 11. Yeah, he's right. So let's see. On my calculator here, check this out if you haven't used this before. I'm going to hit square root, and then I'm going to use the answer button. Mine's an alpha equals. Look for answer. If you don't like having to write all this stuff down, your calculator remembers what the last answer was. That's what I want to square root, so I'm going to go alpha answer, and then it'll put my last answer in there, and I get 10.7. And if it doesn't say, use 1 decimal place, okay? And I'm going to put that on my diagram.
Yeah, you just gotta do the angle.
Now I just got to do the angle. Now, to do the angle, maybe you see another way.
Yep.
But in the interest of teaching, I'm going to do it my way, okay? In the interest of teaching. Then, when I'm done, if you see another way, you can tell me about it, okay? To get that angle here, I'm going to look and go, okay, I've got any sides I want. So I can use any ratio I want because I've got now, I have opposite, I have adjacent, I have hypotenuse. So I'm going to use sine again. I'm going to do sine of C is opposite over hypotenuse. But take a look here. Because I'm using C now, the opposite and hypotenuse are different than they were a second ago. You can feel free to be annoyed by that. But let me help you with that. I want you to just sit here for a second and look at those windows over there. What side are the windows on? Are they on the right side of our classroom or the left side?
The right.
The right. I say they're on the left.
Because you're standing that way. Then.
Because I'm aimed this way. Yeah? If you're looking this way, that's right. If you're looking that way, that's left. That's the same with opposite and adjacent. If I'm looking from A, that's opposite. That's adjacent. I'm looking from C, that changes. So be careful with these labels because they might not always be true. It just depends on what part of the question you're doing. So sine of C is 10.7 over 11.3. How do I get C then? Do the inverse sign. Just like adding has an inverse subtracting, just like multiplying has an inverse dividing, sine has an inverse, the little -1. And it's possible your teacher taught you to first get that as a decimal and then type it in. And that's all fine if you want to do those steps. But maybe your calculator experience has made it so like, well, I don't have to type that in right now. I can let the calculator take care of all that by just using some brackets maybe. And I think on the Casios, it automatically opens a bracket when you hit sine inverse. Am I right about that? When you hit sine inverse, it opens a bracket like, hey, do you want to have a bracket there? It's suggesting maybe a bracket is something you want. On mine, I've got to put a bracket and go 10.7. Try this out in yours to make sure you know how to type it in. 11.3, close the bracket. Equals, I get 71.3 degrees. Okay? That is correct. It is correct. And if you're seeing something else, just relax for just a second, okay? That is the angle. Now, do you see another way that I could have found that angle instead of doing all that, Nathan?
You just make sure that they all add to 180.
Right. Or A plus B plus C equals 180. Do you remember that? They were supposed to beat you up with that in grade 9 a little bit. That the angles add to 180. And so if you do it that way, angle A is 180, subtract the 90, subtract the 18.6, and then you get 71.4 degrees. Sort of freaking you out a little bit. Yeah? Now here's what's happened. By rounding this to 1 decimal place and rounding that to 1 decimal place, those two sides, I wasn't really as accurate as I used to be anymore. And then when I went to do an angle, I got off by 1/10 of a degree. Now let's just make sure we understand how much of 1/10 of a degree is. There's 90 degrees in a right angle. 90 little slices. I couldn't even write an individual degree in here. I couldn't write 90 little slices in here. Then we're talking about tenths of that. This answer's off, but not by much. A decimal degree is like nothing. I don't even know if I could I move my arm 90 little slots? Like, let's try and move my arm 90 slots. 1, 2, 3, 4, 5, 6, 7. I can only maybe do about 15 slots. Degrees are really small. So this answer's off, but not by much. Okay? So don't get excited about that when that happens, if your degrees are off by a decimal point, because it's just not very much. What if you wanted perfect answers? Then I couldn't have rounded off here. See, we rounded off to 10.7 here. I'd have to keep 10.6847. Keep all that. Then when I did Pythagorean theorem up here, so the 3.6, that's when the trouble started. I would have had to write 3.5964, all those decimal places. Then when I got to Pythagorean theorem, kept all those decimal places. And then when I did it over here, I would have got the right decimal place. There's something big going on here about scientific notation and how many decimal places are good and so on. But I'm telling you right now, it's okay to be off a decimal degree, okay? Depending on how you do the question. Any questions about that? That might be completely review all the technical stuff right there. That might be all there was to Socket-Toe and Pythagorean theorem. I'm just going to do a couple extra problems just to do some other things, just to cover all the bases, okay? Next question. In triangle DEF, angle E is 90. So I need another triangle again. And the angle E is the 90. D is 7.4 and F is 6.5. Now this is where the labeling sort of comes in. In the interest of all labeling it the same, if that's big E, we use capitals for angles and we use little letters for sides. So if that's big E, that's going to be little e, the far one across there. This is really going to matter when we go back to do sine law and cos law. Coleslaw. And then the other ones I get to choose. If you draw it differently, you still get the same answers. So if this is going to be F, then this is little f. And if this is going to be, what was my other choice? D. There's big D. There's little d. It's a problem with C's because C and little c look the same, big C and little c. So you got to draw big C, big, and little c, little. There. Now it's all labeled and ready to go. That's the 90. D, I'm putting 7.4 over here. And I'm putting F 6.5 down here. Many choices. Would you like to go after a side or an angle first?
Side's easier.
Side's easier, and I think he's right. This is technically just like a Pythagorean question to get that other side E. So I'm going to go E squared equals 7.4 squared plus 6.5 squared. And you might even do it this way. This is really cool. Don't even type it in until you do the square root, saving you a little bit of effort and writing, because your calculator can handle this, as long as you put that bracket in there. And some calculators automatically come with the bracket. Mine automatically comes with a inside the square root type move, so that I can do 7.4 squared plus 6.5 squared equals 9.85. Now I've gone to 2 decimal places this time, because I've sort of learned my lesson from the last one. If I want everything to be accurate to 1 decimal place, I better carry around 2 decimal places just to make sure it stays accurate. That's not a rule just yet. I'm building towards a rule about how to stay accurate. Anyways, put that on your diagram, 9.85. Next, find an angle. I'm going to go after D. I like to circle them, because I've been teaching this so long that I know people have a problem sometimes if they don't circle the angle they're going to work with and use that to label the sides. So if that's D, this is hypotenuse. This one way over here is going to be opposite, and this one's going to be adjacent for this phase of the question. So I'm going to use tan. Okay, let me just tell you one little thing they probably didn't tell you in grade 10. If you're doing a question like this and you get your choice anyways, only use sides that were given in the question if you can. That keeps mistakes from migrating. Let's say I typed this in wrong and 9.85 wasn't technically right. I made a mistake. If now I go after an angle and use that again, that's going to be wrong too. So to keep the error from cascading, given the choice, I'm going to try to use 7.4 and 6.5 because that's what I was given in the question. So that means I'm using opposite and adjacent. Which one should I use if I want opposite and adjacent? Nathan?
I just have a question.
Yeah.
I can't remember when you're supposed to use the little letters and the big letters.
The big letters are angles. The little letters are sides.
Okay.
And this question does give a hint on that, actually. If you look and go, look at, they used big E for the angle, and they used the little letters. That's not like a rule. That's like mathematicians got together somewhere along the way and went, we got to start doing this all the same, folks. All right? Let's use big letters for angles and little letters for sides, and everybody goes, okay, I'm happy now. And that's why you see in the notes, look at little letters in the Pythagorean theorem, and when you go to do angles, you'll see it's always like big A or big F or whatever. Okay, so opposite and adjacent. If I'm using opposite and adjacent, which one? Tan. Okay, so that's good that you know that. So tan of D is 7.4 over 6.5, and so D is the tan inverse. When you want an angle, you're going to have to use the inverse function. So here I get tan inverse. And again, mine doesn't come up with a nice bracket like that. So I've got to open a bracket if I'm going to put this 7.4 over 6.5 in there. If you're used to writing a whole bunch of decimal points and then writing that down and then doing the tan inverse, hey, that's fine. I'm just offering a shortcut here, is that typing that in and having all those things to write down, your calculator can handle it all. As long as you can handle what you're looking at here, that is tan inverse of 7.4 over 6.5, and I get 48.7 degrees.
Can't you just like add them now?
Yeah, I think the most efficient way now is to stop there and go, okay, if this is 48.7 degrees, I'm not going to go back to SOHCAHTOA. I can just go angle F is 180, subtract the 90, subtract the 48.7. And some people might even have a better shortcut than that, is they might actually go 90 minus 48.7, because they know it's 90. So this other angle's got to add up to 90. You know, so that's even another shortcut. And I think I get 41.3 degrees. And again, decimal degrees is really overkill. That is unbelievably accurate if you're keeping decimal degrees around. So lots of questions will tell you round to the nearest degree, because a degree is already really small. So you don't have to overthink the decimals there. Suffice it to say, on a test, I will be very specific, and usually I go nearest degree and nearest tenth, you know, like 1 decimal place for sides at this level. Okay? Is this all pretty good? Many people smiling. You're happy to be back in the trig chapter. You will be for a while. I don't want to scare you. I'm not trying to scare you. You will be for a while. You'll be quite happy going along with trig here for a little while. Kyle, question?
No,
That's good. Do you need more time here? More time? Yeah. I've already forgotten where this lesson ends.
Are the rest of these questions or just...
Oh, just 2-word problems. Okay, here's 2 things that come up quite often as soon as we bring this out into the real world, is angle of elevation and angle of depression. And this diagram shows them both perfectly. Angle of elevation is the angle between the horizontal for you, for whoever the observer is, up to whatever you're talking about. Angle of elevation goes up, whereas angle of depression goes down, always from the horizontal. So that's key in all this, is that we first have to have, we use a horizontal reference line of whoever's looking. One thing they didn't mention is that if you're going to do that from your eyes, you should be incorporating how tall you are in everything. But we usually skip over that step and go, okay, well, let's just leave that on the shelf for now, and we'll just take what we have, okay? So, does this ring a bell? Now you've got a nice diagram. If it doesn't, for angle of elevation, angle of depression. So 2 quick word problems. Cathedral Grove on Vancouver Island is a rainforest of firs and western red cedars. Irrelevant line. Math questions love stuff like this, where they give you some information that doesn't really matter. From a point 40 meters from the foot of one cedar, the angle of elevation to the top is 65. Now this shows what trig is actually used for inaccessible heights. You can't get up to the top of the tree to measure the height of the tree. However, apparently with a little bit of information, we can use trigonometry to figure it out. That is, if you walked back from the tree, okay, here comes my diagram of the tree. Oh, I don't have a nice green there.
But you only have 2, like, you only have one side and one...
Yeah, I know. It looks impossible. To someone who's never seen one of these before, it looks impossible. In fact, if we went to the woods right now and there's some tall tree there, and let me draw the tree here first. Here comes, here, hang on. Yeah, no, wait. Let me draw the tree. It's going to be a blue tree. Blue tree.
You have all the angles.
Hold on. Tree. Yep, that's my best effort at drawing a tree. Yeah.
You want it back. I know what.
then ground. And again, when people first see this, they believe this is impossible, but this is exactly what trig can accomplish. Somebody looks up and goes, angle of elevation. They find this angle. And should they incorporate their own particular height? And the answer is yes. You would normally incorporate your own height for this angle. But let's just leave that on the shelf for when we're actually doing this. So that's 65 degrees. So what angle was that? They backed up from the tree 40 meters till they saw an angle of 65. Now, let me be clear about this. My father, when he retired, worked as a tree specialist for the last 25 years, going to people's houses, cutting down trees, going into forests, cutting down trees, and he used to do this kind of thing all the time. Only he had a specific method. He'd go out to 45 degrees. He could figure out when the tree was cut down exactly how far it was going to fall out so it wouldn't damage people's houses or damage other trees. So this is like right on top of real world stuff here. So angle of elevation is top of 65 from 40 meters away. So that's all you got to do. Back up 40 meters and use what's called a clinometer. There's a device you can use. You can point it at the top of the tree, and it measures the angle up to the top of the tree. It's not a high-tech thing. It's not a laser-type device. It's just a string and a protractor, basically. And then you get the angle here. And apparently that's enough to get the height of the tree, assuming the tree is going up, straight up, at a right angle. Key moment in the whole thing. Because as soon as you put that right angle on there, then a whole bunch of things come into play. Socket-Toll Pythagorean theorem. And in this case, we have the adjacent side. We'd like the opposite side, so we're talking about tan. Tan of 65 is opposite over adjacent. There, that's the whole deal. The math is actually it's not easy, but it's pretty simple. All we got to do is go 40 tan 65. And I've cleverly switched sides there. If that bothers you, what I really did was I thought of 65, tan 65 as over 1, and I cross-multiplied it. And then I type it in my calculator, 40 tan 65. I almost typed it in wrong. Answer 85.6 meters. Oh, to the nearest meter, they said in the question. 86 meters is about the height of the tree. 85.7. 86 meters. Okay. Do you have any questions about that? Also used in astronomy. You can use this to very accurately measure the distance to faraway stars, faraway planets. All you got to do is wait until you get around to the other side of the planet. So you take a reading on March 21st, take another reading on September 21st, you build a triangle, and you can accurately find out how far away things are. Pretty straightforward stuff. Any questions there? Last one coming up. Need more time here? More time? Yes. Ooh. Good stuff. Folks, we're going to do a lot with this trig over the next few weeks. So don't look at this and go, yeah, I know this so well, won't even do the homework. What a mistake that is. If you know it so well, that's extra motivation to do the homework. Maybe I can get just a great mark in this chapter because I'm good at this stuff, okay? So don't get arrogant here about this stuff. Still more time? No, we're good? Well, here's the killer word problem. This is the one that makes all the grade 10s cry right here. The distance between two office towers is measured using an electronic tape measure at 73 meters. All right, we need 2 office towers this time. Very common grade 10.
So not a triangle?
Here's my picture of the office tower. And then another office tower. You see how I handle this situation? I didn't read the whole word problem. I don't want to be intimidated by reading this whole thing. People get upset when they read a whole word problem like this. They said they had 2 office towers. Boom. I put 2 office towers down.
Why not make them the same size?
Well, because I know the question. I know they're going to be different heights. It's going to be a boring question if they're the same heights. The distance between the two office towers is measured at 73 meters. So this distance here between the office towers is 73 meters. I don't need an electronic tape to figure that out. There's any number of ways to measure along the ground how far away these towers are from each other. So from the ninth floor of the shorter tower, right about there, ninth floor. From the ninth floor of the shorter tower, a clinometer, and again, let's just look up clinometer for a second so you can see this device is not exciting in the least. It's easy to look at this and go, oh, clinometer, I'll need it. I'm going to type in here what a homemade clinometer looks like. I don't know exactly what it's going to show here, but I want to show you that it's a pretty simple little thing that you could use to measure angles. Look at, there's one right there built in a grade 10 class somewhere. A ruler, a piece of string, and a protractor, and you've got a homemade clinometer. You can just look up and just use the string to go, okay, right about there. Yeah? Usually they put a weight on the end of it. Like this one here, they have a weight on the end of it. So pretty straightforward stuff to find these angles. From the ninth floor, a clinometer is used to measure the angle of elevation to the top of the taller tower. Okay, so they found this angle here to the top along a horizontal. They found that angle there, and they found that to be 31 degrees. Let's be clear what I can accomplish right now. I could accomplish right now finding out this distance here, which I will call x. I could do that right now. Next, from the same floor, the angle of depression, shh, stop talking.
I didn't make the cut.
Shh. Angle of depression, 42 degrees. Let's be clear about what I can accomplish now. Using that 42 degrees and the 73 at the bottom, I could calculate, whoops, I don't want to put it there. I'm going to put it here. I can calculate this distance, which I will call y. Is that enough to get the height of the tower?
Yeah.
Yeah, because I can just add x and y at the end. So not that upsetting. I am going to change where the 73 is. I'm going to put it right here. Same 73 right there. And so to do the x, I'm going to go tan 31 equals x over 73, opposite over adjacent. So x is 73 tan 31, which you can get on your calculator if you want. Then if I want to do y, I can go over here and go, oh, tan 42 equals opposite over adjacent. Different angle, so different value. And now down in here, I'm going to find the height. Height equals 73 tan 31, which you could get as a decimal. Go ahead. I like it. Plus 73 tan 42. I'm just going to type that in. Now, if you want to do them separately, if that makes you feel better, I like it. I'm not trying to convince you to do it otherwise. I'm just trying to provide the shortcut. If all of this is like pretty straightforward to you, like, oh, I'm pretty good at this. So that one's 73 tan 31. That one's 73 tan 42. And now my calculator does the rest. 73 tan 31 plus 73 tan 42. Tan 31, tan 42. Someone else type it in. Did you get 109.6? Did someone else type it in?
Yeah, I got that answer too.
Last question. How'd they do this stuff before calculators?
Oh, you use the, like, what tan, like, actually equals?
He's right.
And, like, what, they all equal?
Yeah,
So
no, if you would have got a grade 11 textbook 75 years ago. At the back of the book would be a table that you could look these all up. You'd look up tan 42 and you just look down until you found the answer. So it wasn't that much slower than using a calculator. It was just all on a table set up for you before the course even started. So
Did you like even like solve what tan is? Like
no.
Really? Oh, I thought like.
Why?
No, I assume yeah.
Yeah. You look at me like I'm lying, and I